So I'm Jonathan Graham. I'm going to tell you about the work we've been doing at Los Alamos to attempt to use Legion for multiphysics applications on unstructured meshes. I work for Ristra, which is a research project for Lagrangian hydrodynamics codes. And our main code is Moya. It's a Lagrangian code, so that means that the mesh moves with the material. It supports shocks, gases, solids, and high explosives. The hope being that having the multiphysics code like this will be able to leverage the task parallelism. With Moya, we can model a lot of different physics. This is a Taylor anvil impact problem where a metal rod is fired at an anvil. On the left, from the literature, you can see both the experimental setup and the final state of the metal rod, depending on how fast it's fired at the anvil. On the right are Moya simulation results depicting the strain in the rod. This is a high explosive detonated at 3 points. We're looking at 4 snapshots through time as the shock fronts propagate and interact with each other. The milestone problem for Moya was a shaped charge calculation. A shaped charge is a focused explosive charge used in manufacturing, in the military, and in wells. Our shaped charge is made of 3 parts: an outer steel shell, then the high explosive, and the free surface of the high explosive is lined with a thin lining of copper. On the right is a simulation result from another code. And what you see there happening is along the symmetry axis, a thin jet of copper is formed and it's ejected out the right side. These are the Moya simulation results. So we're looking at pressure, and as we move from left to right, we're seeing the shock front propagate through the high explosive and then reach the focus point where the jet is formed. These are more visualizations of that last time shot where the jet is. So on the right, we're looking at the copper density. And on the left, we're looking at the shape of the mesh cells. So at this point in the calculation, the mesh cells are quite squashed. And to carry on the calculation any further, this mesh needs to be remapped onto a new mesh. The code that's being developed to do that is written on neither Legion nor FlecSI. So when I talk about performance, it's going to be just up to this point in the simulation. Moya is built on FlecSI, which is an acronym for Flexible Computer Science Infrastructure. It's a software layer that sits between the application and Legion. It has a programming model that imitates Legion's. And as the FlecSI, the flexible part of FlecSI is supposed to denote, we've taken a risk mitigation strategy. So this was started in the early days of Legion, and Los Alamos wanted to try Legion without committing to it. So all FlecSI applications can run on either a Legion backend or an MPI backend from the beginning. And recently, they've added an HPX backend. And of course, data parallelism is addressed through Cocos or OpenMP or your choice there. The second main design decision driving FlecSI was the idea of a separation of concerns. In our codes, the physics can be quite cryptic for computer scientists to interpretate, and vice versa. So if we need to modify existing codes, often we need to find somebody with the dual expertise. So the idea with FlecSI is that the physicists can write the physics and the computer scientists can write the computer science. And then additionally, the code will be quickly and easily portable to new architectures. FlecSI is relatively straightforward for a physicist to develop in. They need to define their field types and the access patterns they use in their task functions. And handy wrappers for looping over mesh entities are provided to them. These resolve to Cocos, and so then they can get their data parallelism that way. The execution of a task is a single line of code. So that's our own abstraction that we brought. 2 years ago in October, a small team, pretty much completely new to FlecSI, started writing Moya. By the following May, they had developed the code far enough to make the shape charge calculation that I showed you previously. So to me, this is a testament to how easy it is to develop in FlecSI. The following 2 slides are their takeaways from their experience writing this code. So on the left, all they really needed to do to be able to write their parallel code was to tell FlecSI when they updated their shared cells and what access they needed to their ghost cells. That information was, of course, passed on to Legion, but it was also used to schedule explicitly launched ghost copies, as we'll see in a few slides. And of course, if they have thread parallelism in their loops, they need to take care of that. They don't have to explicitly request communication, which is how they used to develop their codes. They don't have to keep track of their ghost data, whether it's valid or not. And it's very easy for them to move new physics onto GPUs and to move between the various backends that FlecSI provides. This slide is really just a summary of the terminology and syntax that they needed to use. The only other thing that happens here is that FlecSI does track a dirty bit on the shared cells. So I'm going to go ahead and cut to the conclusion, and that is that unlike other Legion applications, we have been struggling to have good performance with FlecSI's Legion backend. I'm going to talk about what's different about us that's leading to that, the history of the progress that's been made on it, and then where we are today. So the big thing that's different is that we use unstructured meshes. Here's the mesh that was used for the shape charge calculation. On the right, you can see a 2D cross-section of it. So we have to deal with complex geometries, and unstructured mesh is the natural choice to take there. And I'm going to show you how that leads to sparse copies. So we're looking at a simple example of an unstructured mesh in 3 colors on the left. On the right, the shared cells are shown in a slightly lighter shade, and all the needed ghost data are in gray. If we line that up in a 1D index space, as on the right, you can see that our data is going to be quite sparse. So what FlecSI does with Legion on the left is make a 2D index space, where each row is one color of the partition. All the exclusive cells are packed together at the beginning, followed by all the shared cells compact, and then the index space is extended or bloated by including a copy of all the ghost data needed for that color. And when the copy launches are made, most of this data in this simple example is compact copies. So we've got chunks of 2 or 1 cells moving to another color. The red arrows show the only sparse copy that's happening. It's not very sparse, and there's only one of them. For our actual meshes, our copies are much more sparse, and there's many more of them. So going to go back in time, I think there's kind of a theme that's been going on. This is a couple years into the project. This was an early version of FlecSI, so there were quite a few limitations. We could only support 1 color per process, and there was no data parallelism. So if we wanted to achieve more usage of the node, we had to run more processes. And what we're looking at here is a ratio of Legion runtime divided by MPI runtime versus the number of cores on a node, and at best, we got 6x slower. This is a very simple application. It's in Eulerian hydrodynamics. There's only 3 tasks, so we can't make up for usage by using task parallelism. What we did instead at this time was come up with a simplified weak scaling experiment. So we know what the solution to using the node resources are, but right now we don't have that, so we're just going to use a single process per node and see how the weak scaling part would play out. This isn't really a comparison, so I'm going to show MPI backend results on there, but that's really just for a baseline to mark our progress against. Because of course, you'd never run MPI with a single process per node. The black triangles are the MPI backend results. And June 20, red, that's the beginning of this, shows how poorly the sparse ghost copies are working in the beginning. And then a lot of work from the FlecSI and Legion team happens. And we moved down to these cyan pentagons, and now we're looking pretty good compared to our baseline. So because of those limitations I just mentioned, and because of quite unwieldy API, FlecSI 1 was rewritten into FlecSI 2. And in these days, we developed another experiment. We wanted to measure the overhead of these sparse copies. So we created a very simple iterative solver. It's Poisson, and there are only 2 tasks. Each of those do very little work, and then there's a couple of other tasks for diagnostics that run periodically. This plot is what I'm going to call an on-node optimization plot, not a strong scaling plot. So we're looking at a fixed problem size, and we're plotting time versus total number of cores, ranks times threads. And MPI backend is in blue. The Legion backend is the orange squares, but the only point of comparison we can really make between these two is from their minima. And we see for the first time in the project, we have the FlecSI Legion backend outperforming the FlecSI MPI backend. And the reason for that is there's a tiny bit of task parallelism happening when we do our diagnostics every 50 steps. Okay, and that's our victory lap. The next thing that happened was the MPI backend was optimized, and now it's faster. So this is a weak scaling plot, time versus number of nodes. The MPI backend is the blue circles, and the Legion backend is the orange squares. So both backends are pretty much scaling the same way, and the MPI backend is maybe 50% faster. So that brings us to today. And today we have Moya, which has task parallelism in it. So this is a profile from a single GPU run of Moya. And I want to point out that no work has been put into fragmenting or fusing the task, any sort of optimization like that. This is just the grouping that made sense to the physicists when they wrote it. And we have overlap. Another on-node optimization because now we have a new code and a new machine and a new version of FlecSI. The Legion backend is in blue and the MPI backend is in orange. It's about 60 to 70% faster than the Legion backend. This is our weak scaling plot. Legion's in blue on the top, MPI's orange on the bottom, and there's about a 2x difference here. Now there's 2 points that I want to make about this 2x, and the first is that the Legion backend is using OpenMP to access more of the cores. And currently, the FlecSI mapper does not allow us to use multiple Legion OpenMP processors, so we can't have our data parallelism and our task parallelism at the same time until that feature is added to our mapper. And the second point is also that the Legion backend is using OpenMP to access more of the cores. And what we saw in earlier experiments, this is back to the Poisson problem, and this is a strong scaling plot time versus total number of cores. If you use MPI everywhere, the blue circles, you get good performance. But if you hamper MPI by using OpenMP with it, the green triangles, that actually accounts for the greatest part of the performance difference between the two backends. This doesn't buy me a whole lot on CPUs because I have to use OpenMP. I don't have a choice, but it makes it an encouragement idea for what's going to happen when we move to GPUs, because then they'll both be using the same data parallelism. Unfortunately, that's not how it panned out. So this is a strong scaling plot on a single node. We're looking at time of a 1 million cell shape charge calculation versus number of GPUs, 1 to 4. And the big thing that's glaring at us is as soon as we move from 1 to 2 GPUs, we have a 10x slowdown. And what's happening here, of course, is we're going back to the sparse gather copies. The realm code to do the sparse gather copies fast on GPUs is relatively new compared to the CPU code. And right now, the FlecSI mapper is not exercising this code path. And we can see that in a profile. Here, all the gathered copies are in the green squares. We're looking at the one highlighted in red, and we see that the copy is taking 3 hops. So it is going through the host. This is turned out to be quite tricky to debug. According to the FlecSI guys, all their instances are where they're supposed to be, and they're seeing some anomalous output from the profiler. So they're thinking, well, maybe there's a bug in the profiler. I know Elliot and us are going back and forth about that. So that leaves us with still several roadblocks to achieving good performance from the Legion backend with Moya. The FlecSI mapper needs more support to achieve performance on CPUs, and we have to debug whatever is going on with the mapper on the GPUs. In hindsight, my opinion is that maybe this bloated index space wasn't the best data structure to use. Maybe we could have dealt with our complex geometries by stitching together several structured meshes instead of making a completely unstructured mesh. For the time being, Ristra is going to take a wait-and-see approach to Legion, and FlecSI is going to continue to work on the performance for their Legion backend. Any questions?